So here's the mini expander that's been taken apart. So what I've already done with this, I've already stripped this board not only of its RF shield, but also of the components on it. If we take a look at the board, it's a pretty simple board. Most of these are just pass-throughs. There are a couple of buffers here that are used to, I would say, increase the signal of the bus between the computer itself. These are really unnecessary if they were much closer, but I guess out of an abundance of caution and because the signal lengths do get a little bit long, they went ahead and put some buffers in here. Over here is some logic for how the sound chip, and I'll actually switch over to my version of the board, well, at least an earlier version of the board. So over here are some logic chips that manage how both the I/O and the sound is handled. This is the sound amplifier. If you ever noticed, when you plug in the mini expander, the volume of the Aquarius goes up. Obviously, there's only one sound channel when you don't have this plugged in, because this disables the onboard sound and then adds 3 new voices of its own. So this is a sound amp. This is a little sound amplification chip. Transistor. On the back, we saw here's the male DB9 pins. Here's the connector pins that allow you to expand a program cartridge and then a RAM cartridge. So this is actually version A, or Rev A, that I did. Well, in the meantime, I'll show you some of the problems that I had on the version. First of all, these are too tall. So what happens is, when you get it in the case, the front door goes down just fine, but the back door hits this trailing edge. So it's important that when you get your cartridge slots, that they be a little bit shorter than this one. The other problem that we run into with this particular one, and these are high-rose connectors. We don't recommend them anymore, even though they're shown on the board silk screen. They're also a little bit too wide here. That's fine for your stock cartridges. They fit on just great. But some of the aftermarket cartridges, like the AquariCart and the 32K expansion cartridge, won't fit over these ends. These actually would have to be trimmed off a little bit. So we don't use the high-rose connectors anymore. All right, let's take a look at the new board. Still the same blue color, but there's a couple of additional things that we've added. First of all, we've added a couple of daughter cards, or I should say breakaway cards here. I'll show you what these are for in a second, and when we actually go through the build, I will show you what those are used for. And we also have a couple of things. I'll see if I can zoom in here. As it sits, you can't put, on the stock mini expander, you can't put 2 RAM cartridges in. Evidently, the system could read both of those and then use those as extended memory. I've never gotten it to work, but evidently you can. So if you wanted to, you could, on our board, solder this jumper and then put RAM in both slots. That's neat. You could also put program cartridges in both slots as well, too. And the difference is how pins 44 and 34 are grounded or not on these. That's the way that cartridges are identified based on their types, whether they are RAM expansion or program cartridges. So if you were to put Tron Deadly discs back here and Night Stalker up here, which one should the system run? Well, in the stock system, which this is wired for, it's going to run this one, the one that's in the front, the program memory slot, and it won't run this because of the way the pins are grounded. But if you decide you want to do that and you want to have the flexibility of putting a ROM in the back or a RAM in the front, you could do that. So that's our new board. These breakaway boards are for the control pad, and the control pad is what we're going to tear down next. Okay, here we have an Aquarius control pad. I've already taken the time to take the screws out of the back, but you've got your cord here. Here's a female DB9. It has 6 buttons on the front, a 16-direction joypad, 4 screws in the back, which I've already taken out, and we're going to lift forward. And we're going to carefully dissect this guy. So first of all, notice that the rubber pads don't have contacts like some systems do. These are just hard rubber things, which is good because it'll make it easier for us to create a replacement for these. 2 sets, 1, 2, 3, 4, 5, 6. We're going to set them aside. So this is the top case, pretty straightforward. We have the control disc itself. It's got a little rotational thing. There is a spring in it, fairly soft press. Its main goal is to keep this pressed up against the inner top of that. In here, and it's going to be really difficult to see, there are a couple pieces of Mylar. The first one, it is kind of a house-shaped thing, and what this does is this keeps this more important piece from getting worn down. It provides a buffer for the spring, and then also when the control pad moves around, this kind of provides a little bit of a gasket, if you will, so that the main board doesn't get messed up. So, this is the connector board, or the interface board. And we're going to lift the whole thing out. Notice there is a little circular disc that sandwiches in between these. That provides a little bit more of a buffer in there, keeps the connections from touching together prematurely, so it provides a little bit of space. So that's the second kind of invisible piece. Here's the bottom. It does have a little turret, rounded turret that this rides in for that. So that's the bottom piece. And here is the control assembly. It is a 3-fold piece of Mylar with conductive ink on the surface. What I've done is I've mapped out all of these connections, and I've put them in a piece which I'll show you in a second. But the conductivity, you put this spacer between the two so that there's a little bit of a gap, so that when you actually do press it, that you're making a connection and it's not touching all the time. The DB9 cable connects via these 9 wires, 9 plugs, so 9 wires, and then it goes to an edge connector, which is actually 10 wires, and I'll show you why. So we're going to pull on this, and there's only wipes on the top part of this. The one we're going to replace this with has them on both sides, but what they've done to make this more sturdy is they've actually folded the plastic over and put a little bit of cement in there to give you something a little bit easier to push this into that. So we'll take a look at this when we get into recreating it. We're going to set this off to the side. And then this is the control cable. It's a female DB9. It does not have screws on the side, and that's very important because the back really doesn't allow room for that. Even though these connectors do have them in it, they're placed too close together for there to actually be lockdown screws. So that's important. You can't just use a very long female-to-female serial connector, even though all the wires go through. The extra tabs just make it unusable. Each of the wires from the cable are broken out into these little connector tabs. And then this is the second half. These replace those. So what you do is, if you're going to be making a cable, well, whether you are or you're not, you're going to be breaking these two pieces off, and these are the connector, control pad interface boards for that. Now, we did say that there are 10 leads within here, and the reason for that is since this Mylar overlay is only a single-sided PCB, for the lack of a better term, it needs to have the ground wire in 2 places, and in this case ground is on 3 and on 7. So if you take a look really closely here, pins 3 and 7 are bridged together, and if you look, it actually skips one of those when they do the wire tie downs. So it's a really simple little board, but it does provide kind of an anchor to the cable. So that kind of exploded is the control pad. Okay, let's talk a little bit about what we would have to do to recreate the Mini Expander and the control pads. Well, the Mini Expander itself is actually pretty straightforward. It is a plastic case, the other half of it's sitting over there. This is a little fiddly. This actually has this cartridge trap door set up here. These are melted in place. They actually have a little bit of a hinge that goes through a metal door. That's pretty fancy. I would imagine that most people would be happy putting just sort of a plug over that if they wanted to do that. This is really not necessary. Plus, as we said before, if you get a connector that's too high, this back door won't even clear that anyway. So we want to try to, in the end, it's just a piece of plastic. We could 3D print this. And the bottom half is actually probably the more important of the two because of these tabs here. Notice they don't really screw into anything, but what they're doing is they are maintaining the pressure right here, 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 and here for when you insert a cartridge. You don't want this PCB to dip and start cracking. So you could, I suppose, put a couple of rubber bumpers that needs to be about 1/2 inch or 3/4 of an inch off of the desktop so that it maintains a level with the Aquarius computer. But what I recommend is actually going the extra mile and at least printing the bottom half so you have something that's going to hold everything in place. So that's that, and it keeps it nice and simple. The PCB is pretty straightforward. I've got designs for that you guys can download and do whatever you want to. The components are fairly easy to get a hold of. These are standard 7400 logic chips. I put mine in chip sockets. If you wanted to save a little bit of money, you didn't need to do that. You don't need to do that. The sound chip, there are old stock versions of it and there's new clone versions of it. They sound a little bit different, but at the end of the day, they do the same thing. They create 3-voice sound, and they also manage the I/O for the joysticks. Everything else are just a bunch of capacitors. This is a line filter, but you really don't need that. You could either put a ferrite bead with 0 ohms of resistance through that to kind of limit some of the noise. But everything else are pretty standard caps, a couple of resistors, and then we have a transistor here that is a fairly standard one. These are absolutely necessary. If you want to have any sort of expansion, you do need these card edge connectors. They go anywhere from about $4 US. I've seen some as expensive as $12 a piece, but they are absolutely required because the whole point of this, if you're going to be taking up your cartridge slot, you need to be able to put something else in it. So those are important. These are kind of important. These through-hole board mount connectors are pretty expensive. These each are actually more expensive than these. These might wind up being more like $12 to $15 a piece. But I have another way that you can get around those. So we did the breakdown of the control pads. Here you can see I have a back piece, a replacement piece for the back that I've done in 3D. I'm still working on the front. It's much more complicated, but if we take a look, this still mates up nicely with that. So that's been taken care of, so I'm still modeling this. But what about the rest of the stuff? Let's take a look at the cable first. Well, we know if you're going to be buying a piece, the PCB, it already has the interface connector boards here. I've got a source for these connectors, and basically the cable that I'm going to recommend using is an Atari /Sega DB9 joystick expander. Some people like the coil. I'll show you how you can do that. Other people just want straight cables. But at the end of the day, you want to make sure there are 9 wires coming out of it and that you've got them mapped to each of the ports. So this we can take care of. We also have a couple of ways to make this a little less expensive. The silicone rubber. This is tough. Fortunately, as I said, we don't have these contacts that we have to put on the inside. They're just there as a means of pushing the control pads up and down. Could you 3D print a hard version of this? Well, I suppose you could, or you may be able to print it in some sort of a flexible filament to do that. That's one way to do it. What I've done instead is I've actually created a mold for these into which I'm going to pour some silicone, squash it so that it will get all of the air out, and then I've basically created a mold to recreate these pieces. The spring, well, if you can find one that's roughly that diameter, which is about 3/4 of an inch diameter, probably about 20 millimeters, and that has a moderate strength. You don't want it to be too difficult, so it's too tight when you're rolling it around. That's pretty easy. The disc can be 3D printed along with the front and back, but the most difficult part is this, and here is here's a laser cut version of the original that I've done. Now this has regular toner on it, and toner is a plastic, so it is non-conductive. In fact, you can't have conductive toner because it won't work in a laser printer. The whole point is that the plastic becomes statically charged, and then it gets melted using the fuser to the paper, or in this case, the mylar. So how do we deal with this? Well, there's a couple of different ways. First of all, we could try and figure out a way to attach a conductive surface to the top. And I've not done this in a while. There are some very, very, very thin foils that are heat reactive that you could put on top of this, put a heat press to, and then kind of like you're doing gold foil, as long as the surface is conductive and you get connectivity or conductivity between here and whatever the endpoints are, it should work great. But you want to make sure that it is fine enough so you can take out the connections between these smaller joints. And in between here, there's some really, really fine ones. The approach that I'm going to take is I'm still going to print this or laser cut this piece on Mylar, as I've done here, along with the two little extra pieces, the house-shaped piece and then the little round gasket that keeps that. That's easy to cut out. But what I'm going to do is I'm going to use a vinyl cutter. I'm going to put a very thin copper foil down, and then I'm going to use a vinyl cutter with a fresh blade to see if we can cut these very intricate pieces. And the way vinyl cutters work is you put it down, it's on a board that has a tacky surface to it, so that when the knife, and it has a little, basically a teeny tiny X-Acto, when it moves around and goes around the corners, there's friction against it. The problem is I don't know how it's going to work on these very fine details. We'll see how that's going to work and if it actually is going to be a good replacement. My backup plan, I'm working with somebody else to create a PCB version of all of this. It'll still use the interface boards, but we'll be interfacing with a pin header rather than with this edge connector that comes in stock. And rather than having a bunch of these pads, there'll be a bunch of tack switches which will be aligned in the 16 positions here for the control pad, and then 6 buttons on top, and they will be wired in a fashion similar to the way these are. Now, how do you get 16 positions out of this? Well, you get it by what's called cording, C-H-O-R-D-I-N-G. If you touch on the top, you have this wire that you can see along with the wire beneath it, which goes up to pad 2. Those get grounded, and that's up, and that's pretty straightforward. Similar to the other cardinal directions, north, west, east, south. They each have a single connection, if you will, that gets grounded, and then the system can read that. It's basically the same way that an Atari joystick works, although I believe the Atari joystick actually has power going through it rather than grounding to it. Okay, that's easy enough. Well, what about the semi-cardinal directions? Northwest, northeast, southeast, southwest. Well, it still has north attached to it, but then it actually grounds out an additional pin, which in this case goes to data, this first data pin there, and you're actually grounding out 2 pins. So it's like you're playing a chord on a piano. Similarly, if you go to north, northwest, which is right here, you're shorting out 3 pins. North, northwest, and then this additional one, you can kind of see the wire that goes up here. So there's a variety of chords that happen. Basically, each of the cardinal directions is a single pin. Northwest, northeast, southwest, southeast, you're grounding 2 pins, and then each of the 8 semi-cardinal directions are actually grounding 3 pins. Like the north, south, east, and west, buttons 1 and 4 ground a single pin. Buttons 2, 3, 5, and 6 ground out 2 pins. And there's a couple of other things, but that's how the magic of the 16 position trackpad works, and it actually does generate 16 unique positions, whereas an Atari joystick isn't going to do that. You can kind of fake an Atari joystick. When you go northwest, you're still pushing north and west, so it does kind of the same thing, but there's an extra layer of distinction within this control pad. Now this is similar to the way, if not almost identical to the way, the Intellivision control pad works. So these are some of the things we need to take into account if we want to create from scratch a mini expander.